Good morning, Dr. Arif. We are Group 3 and we are presenting the Experiment 1, Bernoulli Principle. I am Chong Shun Fu and our group member have To Wan Ting, Lo Wei En, and Ilman. The introduction, what is Bernoulli Principle? Bernoulli Principle states that the total mechanical energy of the moving fluid comprising the gravitational potential energy of elevation, the energy associated with the fluid pressure, and the kinetic of the free motion remain constant. Bernoulli Principle can be derived from the principle of the conservation of energy. The Bernoulli principle formula is a relation between pressure, kinetic energy, and gravitational potential energy of a fluid in a container. The formula of Bernoulli principle is given as follows, which we will later on describe in the theory part. Introduction. The objective of the experiment is to compare the measure and calculated fluid flow velocity in the Venturi nozzle at different points and to investigate the static, total, and dynamic head distribution along the Venturi nozzle. Then, to determine the flow coefficient at the different fluid flow rate. The score is measuring the time taken for a specific volume of water to calculate the water flow rate, investigating the static, total, and dynamic head distribution along the Venturi nozzle, and determine the flow coefficient at different fluid flow rate. The theory part, we use the reference 1 and 2. Bernoulli equation. The Bernoulli equation for constant hash is P1 over rho plus W1 square over 2 is equal to P2 over rho plus W2 square over 2, and is equal to a constant. We taking into account the friction loss and conservation of pressure P1 and P2 into static head water column H1 and H2 given. H1 plus W1 square over 2G equal to H2 plus W2 square over 2 plus head loss. The mass flow rate is constant and in consistent. M1 equal to M2. Given M equal to V times rho, then V1 times rho equal to V2 times rho. So V1 equal to V2, which means given V equal to cross-sectional area times W, then A1 times AW1 equals to A2 times W2 equal to V and V equal to a constant. In this equation, P1 equals to pressure as cross-section A1 and H1 equal to height of water column at cross-section A1. W1 equal to flow velocity at cross-sectional A1. P2 equals to pressure at cross-sectional A2. H2 equal to height of the water column at cross-section A2. W2 equal to flow velocity at cross-section A2. Rho equal to density of medium, constant of incompressible fluid such as water. H loss equal to head loss. Velocity profile in the Venturi nozzle. The Venturi nozzle is used to has 6 measuring points. The table shows the standardized reference velocity, W, which is determined by the geometry of the Venturi nozzle. W equal to A1 over AI. I is the measuring point. Okay. According to the table, the measuring point from 1 to 6 had a cross-sectional area from 3038.6 millimeter square to the measuring point 384.6 millimeter square, and hence the measuring point 338.6 millimeter square, and the W comes from 1 to 4 and back to the 1 again. Calculation of dynamic water column height is H dynamic equal to H total minus H static. Then the velocity W was calculated for measuring dynamic pressure component using the formula. W equal to square root 2 times the difference in dynamic pressure equal divided by the rho equal to square root 2GH. At a constant flow, the initial volume of the calculation of the theoretical volume is given by W1 equal to V over A1. The velocity W1 is then multiplied by the volume of W. Determination of the flow coefficient. The Venturi nozzle is used to flow measurement. The pressure loss that occur are lower than for an orifice measurement. The pressure difference between the inlet and the narrowest diameter of the nozzle is used to measure the flow. V equal to kV times square root delta P over rho equal to kV times square root G delta H. kV volume can be determined from the pressure loss P at a non-flow using the following equation. kV equal to V times square root rho over delta P equal to V over square root G delta H.
So now I will explain about the experimental setup. These are the apparatus that we will use when doing the Bernoulli principle experiment. So this is the overflow, then 7 tube manometer, measuring proof, outer valve, ventrally, water inlet, info panel, and the bleed valve. So figure 5.1 is the Bernoulli principal test bench. So these apparatus I found in the reference tree, which are the lab manual. And for methodology, I also found in the lab manual. First, switch on the main switch and pump. Open the control outlet valve slowly until maximum level to remove the air in the pipe system. Slowly open the black cap valve on the top of the manometer to release all the bubble in the system. Then close the back valve. Close the control valve and the pump. Slowly open the white valve until acting to 100 millimeter. Switch on the pump again. Slowly open the control outlet valve until level of manometer in P1 reach maximum and P3 at the minimum level. Then take the reading and manometer for P static and P total for point P1, P2, P3, P4, P5, and P6 simultaneously, which should record the volume of the water collected at the tank for each point with the time. Then adjust the outlet valve by reducing the flow to determine another reading. So finally, we should repeat the step 7 to 9 with different maximum level and the minimum level.
So now I'm going to present the result of our experiment. For the accuracy of our experiment result, this experiment has been repeated for 5 times with different value of volume flow rate. And each time we recorded down the static pressure and also total pressure for each point with different cross-sectional area. And also we have to calculate the dynamic pressure for each point by using the total pressure minus the static pressure of the typical point. So the first discussion we're going to discuss is the fluid flow velocity in the Venturi nozzle at different points. It can be determined by using the V0 divided by the cross-sectional area, where V0 actually is the volume flow rate, actual volume flow rate at that point we discussed. So this is our calculated result for different value of the volume flow rate and also different value of the cross-sectional area. Also note that even though we use different value of the cross-sectional area and also the volume flow rate, we still get the same result that in point 3, which has the smallest cross-sectional area, will give us the highest value of the flow velocity.
Assalamualaikum, and my name is Muhammad Ilmam. So today I will be starting my part on the discussion part. So I got a discussion for calculate and discuss the static, total, and dynamic heat distribution along the Venturi nozzle. So I take example for Qx equal to 1.5 times 10 of power of negative 4 meter cube per second, which is the time of 20.68 second. I add one example because the flow of the result is the same, but the result is different. But I take for this example. So I will explain to at the next slide. So as you can see at the table before this, for the static pressure, the flow is it decreases consistently from P1 to P3, reflecting the increase in velocity as the nozzle narrows. Significantly increase at P4 where the nozzle begins to widen, causing a deceleration of flow. So number 2, the total pressure remain almost constant across all positions, consistent with the conservation of energy in a steady incompressible flow. The value is between 340 to 390, something like that. So the number 3 is the dynamic pressure. It increases as the flow accelerates through the constricted section of the Venturi nozzle, peaking at P3, drops at P4 due to the deceleration in widening section.
Discussion. This is the question 3, which is calculate the flow coefficient at different fluid flow rates. So this formula I also found in the lab manual. So the flow coefficient can be determined by using this formula. So later I will use the formula which this one. Kv is equal to the dot V over G times the delta H. So dot V is equal to the Q. Okay, so I will use this formula and the field flow rate, which is the QR, is equal to the B, and the flow coefficient, this Kb are calculated. So a higher flow coefficient indicates that a larger amount of fluid is able to pass through the Venturi nozzle with given pressure drops. This explains why the flow coefficient is higher when the QR is higher. So from this table, we can see when the fluid flow rate decrease, then the flow coefficient also decrease.
So in conclusion, the Bernoulli principle experiment show the relation between fluid velocity and also pressure. The fluid velocity is inversely proportional to the pressure, where fluid velocity increase, the pressure decrease. This relation offering a valuable insight to physics when study the motion of fluid.
Okay, next, for safety procedure. First, we must ensure the main switch and pump are properly grounded before starting. Avoid touching electrical components with wet hands to prevent electrical shock. Second is open and close valve slowly to avoid sudden pressure surge. Third is handle the manometer and valve carefully to prevent breakage or leaks. Release air bubble gently to avoid splashing water or pressure imbalance. Fourth is ensure the working area is free of water spills to avoid slipping hazards. 5. Wear safety goggles to protect your eyes. Use non-slip footwear to prevent accidents. 6 is ensure an emergency shut-off switch is accessible in case of system failure. Know the location of first aid kits and inform others of the experiment. 7 is turn off the pump and main switch after the experiment. Drain water from the system and clean up the workplace. And next is the reference. We got 4 reference. We have the Manson B.R. Young Fundamental of Fluid Mechanics. Second is Engineering Label Text, Experiment 2, Bernoulli Theorem Demonstration. And third is the lab manual itself, Faculty of Chemical Engineering, ETM, Fluid Mechanics Laboratory Manual. And fourth is Valencia College, Bernoulli Principal Laboratory Procedures and Analysis.
Okay, this is the appendix of our experiment. Okay. Thank you, Dr. Arif.